Assalamualaikum, students and fellow physics enthusiasts. Today's episode is a sequel of a previous upload, Transverse Wave on a Rope. How do we analyze a sinusoidal wave in terms of the transverse velocity and acceleration of the particles on the rope? Find it out, just watch and learn. The question is, a sinusoidal wave with wavelength 0.400 meter travels along a string. The maximum transverse speed of a point on the string is 3.00 meters per second, and the maximum transverse acceleration is 8.50 raised to the fourth power meters per second squared. What are the propagation speed v and the amplitude capital A, the wave? Here are the given data. The wavelength lambda is equal to 0.400 meters. The maximum transversal velocity of the particle v sub y max is equal to 3.00 meters per second. And we also have the maximum transverse acceleration a sub y max equal to 8.50 raised to the fourth power meters per second squared. The target variables are the speed of the wave propagation, denoted by small letter v, and the wave's amplitude, denoted by capital A. We make use of the quantity k, known as the wave number, which is equal to 2 pi over the wavelength lambda. And since lambda is given, we find k, all right, equals 2 pi divided by 0.400 meter, or the wave number k is equal to 15.7 radians per meter. The angular frequency omega is also equal to the product of the wave number k and the speed of the wave propagation. That is, omega equals k times v. Hence, we can also express omega in terms of the wave speed v, all right? That is, omega is equal to 15.7 radians per meter multiplied by v. V is one of our target variables. This is the displacement graph of the transverse vibration of the particles in the string, or a snapshot of the shape of the string at time t equals 0. So we select and describe particles A, B, C, D, and E. When a particle is at the equilibrium position y equals 0, just like particles B and D, okay, the velocity of the particle is maximum, right? Either positive or negative. And the acceleration at this position is 0 because the net force acting on the particle is 0. At the maximum positive, or negative displacement, velocity v sub y is 0, and acceleration a sub y is maximum. Alright? Acceleration is negative for a positive displacement, just like particles A and particle E. Alright? And the transverse acceleration is positive for a negative y displacement, just like particle C. Alright? Now, the velocity of the wave propagation is emphasized here as being directed, alright, from left to right. We also emphasize, again, that this wave is considered transverse because the vibration of the particles is perpendicular to the velocity of the wave propagation. Now, the wave equation for displacement y, alright, as a function of time is equal to the amplitude capital A times the cosine of the phase angle quantity kx minus omega t. Alright? The minus sign inside this parenthesis is for the wave that is moving to the positive x direction, just like what we have here in the graph. Now, we use the plus sign if we know that the direction of the wave propagation is negative, meaning from right to left. Alright? Also, the wave equation here is just one of the several ways of expressing the wave function. Alright? We make use of the wave number k and the angular frequency omega instead of what we had in our previous episode where the wave functions were expressed in terms of the wavelength lambda and the period capital T. Alright? This equation is used if you want, for example, to determine, alright, the displacement of any particle x and at any given time. But in this graph, we are referring to, for example, x equals 0. In other words, the particle at the maximum y displacement, such as particle A. So if x equals 0, at time 0, all right, what do you think will be the y displacement of that particle? All right, so all we need to do is just substitute the x, all right, and the time t. All right, so at x, or for x equals 0, all right, and at time equals 0, we say that the y displacement of particle A is in fact equal to the amplitude capital A and the cosine of 0, which we know is equal to 1. So in short, all right, the y displacement of that particle, particle A, is just equal to the maximum displacement, or exactly equal to the amplitude of the wave. Alright? So we can do the same thing for any value of x. Alright? Such as particle B, particle C, particle D, particle E. Alright? And at any given time. That is the equation to use. Likewise, we also have a corresponding equation to determine the uh, transverse velocity of any particle at any given time. And the equation for that is Vy, all right, is just equal to omega multiplied by the amplitude capital A and the sine of the phase angle. All right, the quantity inside the parentheses is called the phase angle. All right, so uh, in our example or in our situation, okay, we are referring to the particle that is or that has the maximum displacement, particle A. All right, so if x is equal to 0, okay, what is the instantaneous velocity of that particle at time equals 0? All right, so using this formula, we just substitute, all right, uh, x equals 0 and time equals 0. All right, so the phase angle inside the parentheses, of course, will be equal to 0 radian. And the sine of 0, of course, is equal to 0. All right, so it agrees, all right, it agrees with our earlier description that the instantaneous velocity of a particle at the maximum displacement, such as particle A, particle E, and particle C, all right, these particles have the transverse velocity v sub y equal to 0. And last but not the least, we also have the corresponding equation for determining the transverse acceleration a sub y. All right, and the formula is simply a sub y equals the negative of the square of the angular frequency omega multiplied by the amplitude capital A and the cosine of the phase angle quantity kx minus omega t. Notice that A cosine quantity kx minus omega t is just in fact, okay, the expression for uh, the y displacement. All right. There is a negative sign here to emphasize the fact that uh, the transverse acceleration is always opposite in direction to the amplitude. All right. For instance, going back to our illustration, particle A has a negative transverse acceleration because it is located, all right, in the positive displacement y, all right, and emphasize that here by the arrow colored green pointing downward towards the equilibrium position. That's also true for particle E. All right, particle E is also at the positive maximum displacement, so its transverse acceleration is also negative and has a maximum value or magnitude. All right, but in the case of particle C, the acceleration is said to be maximum but positive. And that is emphasized by this green arrow pointing towards or upward towards the equilibrium position. So that's in fact the meaning of the negative sign in our equation here. So just like what we did for y and for v, let's determine what do you think is the transverse acceleration of a particle x equals 0, meaning particle A as well as particle E. All right. So if x equals 0, at time equals 0, the transverse acceleration, okay, will be equal to, all right, negative omega squared multiplied by a cosine 0. All right. And the cosine, again, cosine of 0 radian is equal to 1. So it means that the transverse acceleration of particle A as well as of particle E is maximum. all right, equal to negative omega squared times the amplitude A. Earlier, we already said that the wave number K is equal to 15.7 radian per meter. We can find the angular frequency omega in terms of the wave number K and the wave speed of propagation, small letter v. So, the angular frequency omega is just equal to K times B. Alright? So, substituting the value of K, we'll get omega equals 15.7 radian per meter multiplied by small letter v, or the speed of the wave propagation. Alright? This formula for relating the angular frequency and the speed of the wave propagation, alright, is true for any periodic motion, alright, such as what we are discussing now. Now, when a particle is at the equilibrium position, alright, its B sub y is said to be maximum, alright, and the formula for B sub y max in terms of omega and A is this, alright? B sub y max is simply equal to the product of the angular frequency omega and the wave's amplitude, alright? Because earlier we noted that if a particle is located in the equilibrium position, then we say that its vertical displacement is zero, alright? So, at the equilibrium position, okay, the transverse velocity of any particle, okay, within the string, okay, is considered maximum. All right? And this can be equated, all right? The B sub y max can be equated to the wave number k multiplied by the speed of wave propagation and the amplitude capital A. All right? And since our target variable or variables are v and the amplitude A, all right, we will isolate capital A, or the amplitude of the wave, and come up with this first equation, or equation number one. All right, we are given the maximum v sub y equal to 3.00 meters per second, and that will be divided by the product, all right, of the angular frequency omega, which we express as 15.7 radians per meter multiplied by small letter v, or the speed propagation, all right, of the wave. So, equation 1 contains two unknown variables, the amplitude capital A and the wave speed of propagation, small letter v. All right. Also, we are given the maximum transverse acceleration a sub y max. All right. So, a sub y max is the acceleration of any particle that has a displacement equal to the amplitude of the wave. All right. And a sub y max, or the transverse acceleration of any particle located at the maximum displacement, is related to the angular frequency omega and the amplitude a in this equation. So a sub y max is just equal to the square of omega multiplied by the amplitude a. Again, we can express this in terms of the wave number k, all right, as well as v, the wave speed of propagation. That is, a sub y max is also equal to negative k squared v squared multiplied by the wave's amplitude, capital A. And again, we can isolate the amplitude, capital A, all right, for us to come up with equation number 2. So, with amplitude A isolated, that can be expressed as the what we call the acceleration, that is given as 8.50 raised to the 4th power meter per second squared. All right, and that will be divided by, all right, the square of the value of k multiplied by the square of the speed, small letter v. Okay, we already discarded the negative sign. Okay, when we substitute the square value of k in this formula, okay, we disregarded it because the only purpose of the negative sign in this formula is that we want to emphasize that the acceleration a sub y, all right, always has the opposite direction of the displacement. So when we're talking about a positive a sub y, it follows that the displacement is negative a, or that the amplitude that we are referring to is the one that is in the negative or maximum negative displacement. All right. So since we're only after the magnitude of the amplitude, all right, strictly speaking, amplitude is always positive. So that's the reason why we already ignored the negative sign here. So once again, these are the two equations, equation 1 and equation 2. In just a short while, we are going to determine these two unknown variables, all right, or target variables, uh, capital A, or the amplitude of the wave, and the wave speed, small letter v, wave speed propagation. Equating these two equations, 1 and 2, we will have uh, the following, all right. So in the first equation, we have 3.00 meter per second divided by 15.7 radian per meter, okay, multiplied by the speed v. That's equated to equation number 2, 8.50 times 10 to the 4th meters per second squared divided by the square of 15.7 radian per meter, all right, and multiplied to the square of the unknown variable v. And simplifying, all right, so this is the simplified equation now, and Eventually, we will get the value for the wave speed of propagation, small letter v, which is equal to 1.80 raised to the third power meters per second. Take note that we followed the rules significant figures in our operation. To find the wave amplitude, we use this equation, equation number 1, and we just substitute the computed value for the speed of wave propagation, small letter v. All right. So the value of, or computed value of small letter v is 1.80 times 10 to the third power meter per second. All right. So doing our math to find the amplitude capital A, we get the amplitude equal to 1.06 times 10 to the negative 4 meters. All right. So this is the amplitude of the wave. Again, we followed the rules of significant figures. Now for our evaluation, okay, we can actually check if our computed amplitude capital A will come out the same as this, okay, by using equation number 2. All right, this is equation number 2. So all we need to do is also substitute the computed value for the speed of the wave propagation, v. That is, all right, this is the value of the a sub y, or the transverse acceleration, all right, and that will be divided by the square of 15.7 radian per meter, which is in fact 246.5 meters per meter squared, and also the square of the computed speed of the wave propagation. Okay, the square of 1.80 raised to the third power meter per second is of course 3.24 times 10 to the 6th power meter squared per second squared. All right. So simplifying this, we get the same value for the amplitude, equal to 1.06 times 10 to the negative 4 meters. And that concludes our tutorial. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.